There's an object approaching from the Oort Cloud that's larger than some asteroids we worry about, and absolutely nobody is worried. That should bother you. UN 271 is the size of a small mountain range, and right now it's being hammered by solar wind conditions it hasn't experienced in millions of years. The strange part? It's responding, outgassing, activating, doing things 14 years before its closest approach to the sun. Scientists didn't predict this. The models didn't account for this. And if a 140-kilometer ice ball can surprise us this badly, what else are we missing? Stick around, because by the end, you'll understand why the biggest comet ever found might become the most important thing. Astronomy studies this decade. Subscribe and follow along, because what unfolds next will determine whether early activation was a fluke or a fundamental misunderstanding of how large bodies behave. Because when timing, geometry, and stellar violence converge to crack something that survived 4 billion years, that's not random. That's a stress test we didn't design. And we're about to see if the structure passes. Right now, something ancient is waking up, far earlier than any model predicted. Out beyond Saturn's orbit, in a region of space where sunlight arrives weak and diffused, a comet the size of a small mountain range has begun to stir. This shouldn't be happening. Not yet. Not here. Not at this distance. But the instruments don't lie, and the data keeps streaming in, and every observation confirms what was initially dismissed as instrumental error. See 2014. UN 271, known more elegantly as Bernardinelli-Bernstein after its discoverers, is active. Violently, unexpectedly, impossibly active. You need to understand something about this object first. This isn't some ordinary dirty snowball tumbling through the outer solar system. Hubble measurements combined with ALMA radio observations have confirmed what astronomers initially struggled to believe. The nucleus of this comet measures somewhere between 120 and 140 kilometers across. That's not a typo. We're talking about an object roughly the width of the distance between Los Angeles and San Diego, composed primarily of ice and rock, hurtling through space at tens of thousands of kilometers per hour. It is, without qualification, the largest comet nucleus ever measured by human instruments. The story of where this thing came from is almost as remarkable as what it's doing now. UN 271 originated in the Oort Cloud, that theoretical sphere of icy bodies surrounding our solar system at distances so remote they're measured in light months rather than astronomical units. These are the relics, the leftovers from the solar system's formation 4.6 billion years ago. Objects that have remained essentially unchanged, frozen in time, untouched by the sun's influence. This particular giant has been making a slow, lazy orbit that takes millions of years to complete. And now, for the first time in recorded history, it's coming back. Its closest approach to the sun won't happen until 2031. At that point, it will still be 10.9 astronomical units away, which places it beyond the orbit of Saturn. For comparison, Earth orbits at 1 astronomical unit. This comet will never come anywhere close to threatening our planet. It will never develop the spectacular tail that makes comets famous in popular imagination. By conventional standards, its perihelion passage should be, frankly, unremarkable, except it's already behaving in ways that defy conventional understanding. ALMA radio telescopes detected carbon monoxide outgassing from UN 271 at distances exceeding 15 astronomical units from the sun. Carbon monoxide sublimates at incredibly low temperatures compared to water ice. But most comets, even those with substantial carbon monoxide reserves, remain dormant at these extreme distances. The energy input from the sun this far out simply isn't sufficient to drive the kind of activity we're observing. Or at least, that's what the models told us. The models, it appears, were incomplete. Now add another variable to this equation. The sun is approaching solar maximum, that phase of its 11-year cycle when magnetic activity peaks, when solar flares become frequent, when the solar wind grows turbulent and unpredictable. The sun isn't a static lamp illuminating the solar system evenly. It breathes. It pulses. It hurls plasma and electromagnetic radiation in complex, dynamic patterns that vary not just by the day, but by the hour. During solar maximum, the heliosphere, that bubble of solar influence that surrounds our entire planetary system, becomes chaotic. The solar wind's velocity and density fluctuate wildly. The interplanetary magnetic field, which is embedded in the solar wind, writhes and twists, and objects at the outer edges of the heliosphere, objects like UN-271, experience conditions they would never encounter during the sun's quieter phases. Here's where the geometry becomes crucial. In early 2026, UN-271 occupies a position directly beneath the planetary plane. It's not protected by the magnetic complexities that objects near the ecliptic experience. It's exposed. Think of the heliosphere not as a static shield, but as a breathing bubble with variable thickness and permeability. Some regions offer more protection than others. Some orientations of the interplanetary magnetic field couple more efficiently with objects than others. Scientists who study Earth's magnetosphere have known for decades that southward-oriented interplanetary magnetic fields are particularly effective at coupling with planetary magnetic fields. These southward configurations allow solar wind energy to penetrate more deeply, to interact more violently. Whether this same principle applies to comets, which lack intrinsic magnetic fields, remains an open question. But the timing is suggestive. Troublingly suggestive. Reports from solar observation networks have documented elevated solar wind conditions, clusters of enhanced plasma density and velocity, occurring in patterns that some researchers have privately begun calling the triple plasma burst phenomenon. Whether these constitute discrete events or merely fluctuations in an already turbulent solar wind is still debated. But their timing correlates precisely with the period when UN-271's activity began accelerating. We are not watching classic solar heating drive cometary activity. This is something different. This is energy interaction happening years before it should, in a configuration that wasn't supposed to matter, affecting an object that wasn't supposed to respond. Astronomers love to talk about surprises. Comet Ison surprised everyone by disintegrating before its solar flyby in 2013. Comet Linear shattered unexpectedly in 2000. Comet Kohoutek disappointed observers in 1973 by underperforming predictions. But none of those objects were this large. None were this distant when they became active. None were caught in this particular cosmic crossfire between a waking giant and an angry star. The question that keeps circulating through research groups, the question that appears in private emails and late-night conference calls, is simple and terrifying in its implications. If UN-271's ancient pristine crust is already responding to solar conditions this far out, what happens when it gets closer? What happens when the energy input increases by orders of magnitude? What happens when billions of years of structural integrity meet 21st century solar violence? Are we witnessing the opening act of a long, slow transformation? And if this crust fails now, before the main event, what exactly reaches 2031? Size in space doesn't mean what you think it means. Your intuition tells you that bigger objects are stronger, more stable, more resistant to forces that would tear smaller bodies apart. On Earth, this intuition serves you well. Massive buildings withstand earthquakes that would flatten smaller structures. Large ships ride out storms that would capsize dinghies. But space operates on different rules, and for cometary nuclei, being large isn't an advantage. It's a vulnerability. UN-271 isn't a solid chunk of ice and rock. Nothing that large, formed in the outer solar system, could be. Detailed studies of comets visited by spacecraft, particularly the Rosetta mission's intimate examination of Comet 67P, have revealed the truth. These objects are rubble piles, collections of smaller fragments loosely bound by gravity and sintered together by billions of years of micro-collisions and ice fusion. The tensile strength of these structures is pathetically weak. You could probably punch your fist through a cometary nucleus if you could somehow stand on one. They hold together not through structural integrity, but through mutual gravitational attraction and the slight cohesion provided by ice acting as a weak cement. Now scale that fragility up to 140 kilometers. Imagine a frozen lake, but instead of meters thick, it's the size of a mountain range. Now heat it from one side. The surface responds immediately to the energy input. Ice begins to sublimate. Gases begin to escape. But that energy takes time to conduct into the interior. The inside of the comet remains frozen while the outside warms. This creates differential thermal stress. Regions of the nucleus expanding while other regions remain contracted. Tension building across boundaries between warm and cold material. This is thermal lag, and it's a killer of comets. Billions of years of exposure to cosmic rays have done something else to UN 271's surface. High-energy particles striking ice cause chemical changes, creating a hard, sintered crust. It's like the difference between fresh snow and the hardened ice that forms on top of a snow pile after weeks of freeze-thaw cycles. This crust is rigid, brittle, and strong enough to trap volatiles beneath it. For millions of years, this was fine. The crust did its job, protecting the pristine interior from the minimal energy input of distant starlight. But now conditions are changing. Carbon monoxide ice doesn't behave like water ice. It sublimates at temperatures around negative 205 degrees Celsius. Carbon dioxide follows at slightly warmer temperatures. Both gases are present in cometary nuclei, mixed with water ice and silicate dust. As solar energy input increases, even slightly, these supervolatiles begin their phase transition from solid to gas. And gases, unlike solids, require space. They build pressure. They seek escape routes. They push against whatever confines them. Beneath UN 271's hardened crust, pockets of volatile material are beginning to sublimate. Gas pressure is building in cavities and voids within the rubble pile structure. The crust holds for now. But every thermal cycle, every exposure to enhanced solar wind, every fluctuation in energy input weakens it further. Microscopic cracks propagate. Stress concentrations develop around irregularities in the crust's thickness. What makes this situation unique is timing. UN 271 is experiencing structural stress years before its perihelion passage. The early activation we're witnessing may be pre-weakening the nucleus, creating failure points that will catastrophically release when the comet reaches higher energy environments closer to the Sun. Or it might trigger failure now, in slow motion, over the next several years. Consider Hale-Bopp, one of the largest comets observed in modern times. Its nucleus was estimated at roughly 60 kilometers, less than half UN 271's diameter. It activated much closer to the Sun and performed more or less as models predicted. Comet Ison, smaller still, fragmented spectacularly as it grazed the Sun at 0.7 million kilometers. But Ison's failure was concentrated, violent, and quick. The thermal stress was applied rapidly in the Sun's immediate vicinity. UN 271 faces something different. The stress it's experiencing is distributed over years, applied gradually, affecting a structure orders of magnitude larger than anything we've observed fragmenting before. We have no precedent for this. The models don't extend this far. The reference cases don't exist. ALMA observations have detected something else troubling. The carbon monoxide emissions aren't uniform across the nucleus. They're asymmetric, concentrated in specific regions. This suggests localized vents, jets of gas escaping from discrete failure points rather than a general, uniform sublimation across the entire surface. Jets indicate concentrated stress release. They indicate that the crust has already begun to fail in specific locations. When a comet develops non-radial jets, when gas escapes preferentially from specific points rather than uniformly, it creates uneven thrust. This can alter the comet's rotation. Slowly perhaps, but measurably. Changes in rotation rate create new stress patterns. Material wanting to fly off due to centrifugal force meets material held together by gravity and ice cohesion. Something has to give. Here's what keeps researchers awake at night. If this object fails, it won't explode. Explosions require concentrated energy release, chemical reactions, or sudden volatile expansion. UN-271 isn't a bomb. It's a weakened structure under increasing stress. When it fails, if it fails, it will unravel. Layers will peel away. Sections will detach. The process might take months or years, a slow-motion disintegration playing out across astronomical distances. And what does unraveling look like on a 140-kilometer scale? What does it mean when the largest comet nucleus ever discovered stops being a single object and becomes a population of fragments, each potentially large enough to be considered a comet in its own right? That's not a hypothetical question anymore. It's a forecast. The models we use to predict comet behavior were built for smaller bodies. Most cometary science, most of our understanding about how these objects evolve and fragment, comes from studying nuclei 10 kilometers across or smaller. These are the comets we've encountered with spacecraft, the ones we've observed fragmenting, the ones that dominate the historical record. And for those objects, our models work reasonably well. We can predict coma development, estimate gas production rates, forecast orbital evolution with acceptable accuracy. UN-271 is 14 times wider than those comets. Volume scales with the cube of radius. We're talking about an object with more than 2,000 times the volume of a typical comet nucleus. And physics doesn't scale linearly. Gravitational self-interaction becomes significant. Internal pressure gradients become important. Structural failure modes change fundamentally when you transition from house-sized objects to mountain range-sized objects. There are two basic ways a comet can fragment. The first is sudden catastrophic breakup. This happens when a comet passes too close to a massive body and tidal forces rip it apart, or when thermal stress near the sun overwhelms structural integrity so quickly that the nucleus shatters. We've seen this. Comet Shoemaker-Levy 9 fragmented tidally before impacting Jupiter in 1994. Comet Ison likely shattered from thermal stress during its solar flyby. But UN-271 isn't experiencing tidal stress. It's not approaching the sun closely enough for thermal stress to cause sudden breakup. What it's experiencing is something more insidious, more gradual, progressive delamination. Imagine an iceberg, but instead of floating in water, it's tumbling through space while being gently heated on one side. The surface layers warm and weaken. Cracks develop along boundaries between different ice compositions. Gas pressure from sublimating volatiles pushes against these weakened zones. Eventually, a section detaches, not explosively, but almost gently, like a calving glacier releasing a chunk of ice into the ocean. Now repeat that process over months or years. Not all at once, not catastrophically, just persistent, progressive loss of material from a structure that was already barely coherent to begin with. The fragments that detach won't necessarily escape UN-271's gravitational influence immediately. An object this massive creates a meaningful gravitational well. Fragments could remain loosely bound, orbiting the main nucleus, creating a debris cloud that travels together along the original orbital path. This has been observed in smaller comets. UN-271 could develop an entire family of subsidiary bodies, a swarm moving information through the outer solar system. Here's where carbon monoxide creates additional problems. Gas-driven activity can outrun dust cohesion. When volatiles sublimate and escape, they drag dust with them, but only up to a point. If gas production is high enough, if the escaping material moves fast enough, dust particles can't keep up. They fall back. They settle into voids left by departed ice. These voids weaken the structure further. It's a positive feedback loop. More activity creates more voids. More voids enable more activity. More activity accelerates fragmentation. Rotation adds another variable. When material leaves a comet asymmetrically, it creates uneven thrust, like a rocket engine firing at an angle. This can change the nucleus's spin rate. For a large object, even small changes in rotation can create significant centrifugal stress. Material at the equator of a rapidly rotating nucleus experiences outward force. If that force exceeds the weak cohesion holding the rubble pile together, material simply flies off. This is called rotational breakup, and it's been observed in asteroids that spin too fast. Could UN 271 spin itself apart before it even reaches perihelion? The data isn't sufficient to rule it out. If fragmentation occurs, if UN 271 evolves from a single nucleus into a distributed population of debris, those fragments continue along roughly the same orbital path. Some will move slightly faster, some slightly slower, depending on the velocity they acquired during separation. Over time, this creates a ribbon of material strung out along the orbit, potentially extending millions of kilometers. This debris ribbon could persist for years, possibly decades. Material beyond Saturn's orbit experiences minimal drag. There's no atmosphere to slow things down, no planetary gravitational perturbations strong enough to scatter the fragments widely. The population would slowly disperse, but it wouldn't disappear. And here's something most people don't consider. Dust in space isn't inert. It interacts with the solar wind. It carries electric charge. It responds to electromagnetic forces. A large population of charged dust particles, distributed across millions of kilometers, creates a local modification to plasma flow. It's a small effect, probably not detectable unless you're looking for it, but it's real. Scientists don't often discuss this publicly because it sounds like speculation, like the kind of wild theorizing that undermines credibility. But privately, in research groups with access to the data, the conversations are happening. What does a fragmenting 140-kilometer comet nucleus actually look like? How much material can it shed? How long does the process take? And what, if anything, can we observe from Earth as this unfolds? The honest answer is, we don't know. We've never seen anything like this before. We're extrapolating from smaller objects and hoping the physics doesn't contain surprises. But comet science is built on surprises. Every major comet mission has revealed something unexpected. Every close encounter has challenged our models. Why should UN 271 be different? Here's the deeper question, the one that shifts perspective entirely. At what point does a comet stop being one object and start being a population? If UN 271 sheds 10% of its mass as fragments, is it still UN 271? If it becomes a cloud of debris with one large central body, do we still call it a comet? The universe doesn't care about our naming conventions. The physics continues regardless. But it raises something unsettling. Maybe we've been focused on the wrong actor in this drama. Maybe the comet isn't the protagonist here at all. We tend to think of the sun as a passive heat source, a lamp illuminating the solar system, driving comet activity through simple thermal radiation. That's profoundly wrong. The sun is a dynamic, violent, magnetically complex plasma ball that continuously hurls matter and energy into space at speeds exceeding 1,000,000 kilometers per hour. It doesn't just heat comets. It sculpts them, interacts with them, couples to them through mechanisms we're still working to understand. And during solar maximum, when magnetic activity peaks, when the sun's behavior becomes unpredictable and chaotic, that interaction intensifies dramatically. Solar maximum isn't just about more sunspots or more frequent flares. It's about fundamental changes to the structure of the heliosphere. that vast bubble of solar influence extending far beyond the planets. During the Sun's active phase, the heliospheric current sheet, which is essentially a ripple in the Sun's magnetic field structure extending outward, becomes warped and complex. The plasma sheet, a region of higher density solar wind material, varies in thickness and position. These aren't subtle changes. They're the difference between a smooth flow and turbulent chaos. Objects at the outer edge of the heliosphere experience conditions they simply don't encounter during solar minimum. The solar wind's velocity can fluctuate by hundreds of kilometers per second over hours. The plasma density can spike by factors of 5 or 10. The magnetic field orientation embedded in that plasma rotates and reverses unpredictably. Now consider how this affects a comet. When solar wind plasma encounters a comet's coma, the cloud of gas and dust surrounding the nucleus, it doesn't just blow past. It interacts. The solar wind carries the sun's magnetic field with it. That field can couple to ionized gas in the coma, creating electric currents, generating forces that shape and direct the comet's ion tail. This is well-established science. We've observed it for decades, but here's what's less discussed. The directionality of this interaction matters enormously. A solar wind stream approaching a comet head-on creates different effects than one approaching at an angle. A magnetic field oriented southward, anti-parallel to the local field structure in the coma, couples more efficiently than one aligned parallel. It's not just about energy. It's about geometry, orientation, coherence. Think of it like the difference between a focused water jet and a diffuse mist. Both deliver water. Both carry energy. But the jet cuts, while the mist merely dampens. Solar wind conditions during maximum can create focused streams, coherent structures in the plasma, regions of enhanced coupling that affect comets far more than the simple average energy would suggest. There's emerging research, still in its early stages, still controversial, suggesting that plasma interaction can feed back into surface activity. The idea is that ion tail dynamics, the forces exerted on escaping gases by the solar wind, can influence where and how gas escapes from the nucleus. It's a coupling mechanism, a way for solar conditions to directly sculpt cometary activity rather than just responding to it. If this mechanism exists, if solar wind coupling can precondition comet failure, then UN-271's early activation makes even more sense. The enhanced, directionally variable solar wind during maximum could be actively weakening the structure, creating preferential failure points, essentially pre-fracturing the crust years before thermal stress from closer solar approaches becomes dominant. This is speculative. It needs to be stated clearly. We don't have proof of electromagnetic sculpting of cometary jets. We don't have confirmed observations of plasma pinch effects influencing outgassing patterns. But we do have observations that don't fit classical thermal models. We do have activity occurring where it shouldn't, in patterns that correlate suspiciously well with solar wind conditions. Scientists hate saying we don't know in public. It sounds like weakness, like uncertainty undermines authority. But good science thrives in uncertainty. The best discoveries come from phenomena that don't fit existing models. And UN-271 doesn't fit. What makes this object unique isn't just its size, or its distance, or its timing individually. It's the combination. A 140-kilometer nucleus, experiencing enhanced solar wind conditions during maximum, positioned outside the planetary plane, where magnetic shielding is minimal, approaching its first perihelion passage in millions of years. It's a natural stress test for heliophysics models, a living experiment in star-comet interaction, playing out in real time. And if the sun is the sculptor, if solar conditions are actively reshaping this ancient object, then fragmentation isn't a failure of the comet. It's a success of the star. The sun is doing what stars do, extending their influence, imposing their will on matter within their domain. There's no intelligence behind this, no intent. Just physics, played out on scales and timescales that make human intuition completely useless as a guide. But understanding that physics, mapping those interactions, observing how a star reshapes a pristine remnant from the solar system's formation, that has value beyond simple description. Because destruction in astronomy often means access, and if UN-271 fragments, if it exposes its interior to our instruments, we gain something precious, something we could never obtain any other way. The question is whether that gain outweighs the loss. There's a reason astronomers get excited about comet fragmentation despite the destruction it represents. When a comet nucleus breaks apart, when sections of the interior become exposed to space and to our instruments, we gain access to material that has been locked away, unchanged, for billions of years. Comets are time capsules. Their interiors preserve chemical signatures from the solar system's formation, isotopic ratios that tell us about temperature and pressure conditions in the early solar nebula, organic molecules that might have seeded Earth with the precursors to life. But accessing that interior has always been a problem. Spacecraft missions are expensive, rare, and limited to a handful of targets. Ground-based spectroscopy can only analyze surface material and gases in the coma. The nucleus interior remains hidden, protected by meters or kilometers of overlying ice and dust. Fragmentation changes that. When UN-271 sheds material, when chunks of the interior break away and develop their own comas, those fragments become distributed probes. Each piece of debris exposes fresh material to sunlight and to our spectrographs. Chemical gradients that exist within the nucleus, variations in composition between the surface and interior, become observable. We get to sample material that formed at different temperatures, different times, potentially different locations in the early solar system. The scientific payoff could be extraordinary. Isotopic ratios of hydrogen, oxygen, nitrogen, and carbon tell us about the temperature and radiation environment where the comet formed. Did UN-271 form in the outer solar nebula where temperatures were low and ice dominated? Or did it form closer in and get scattered outward by planetary migrations? Isotopes answer those questions. Organic compounds preserved in cometary ice include amino acids, the building blocks of proteins, and complex carbon molecules that could serve as precursors to biochemistry. Earth's water might have come from cometary impacts during the late heavy bombardment. The organic chemistry of life might have been delivered the same way. Understanding cometary composition isn't just astronomy, it's origins research. But there are downsides. If UN-271 fragments extensively, if it becomes a distributed population rather than a single object, mass estimates become uncertain. You're no longer measuring one nucleus. You're trying to account for dozens or hundreds of fragments, many probably too small to resolve individually. Total mass, which is crucial for understanding the comet's dynamical history, becomes ambiguous. Orbital prediction becomes harder too. A single massive nucleus follows a predictable path. A swarm of fragments, each potentially experiencing different non-gravitational forces from outgassing, spreads out along the orbit. Some pieces accelerate slightly, others decelerate, the population disperses. Tracking individual fragments becomes impossible beyond a certain point. And there's a philosophical dimension that's harder to quantify. UN-271 has existed as a coherent object for likely billions of years. It survived the solar system's violent early history. It orbited in the Oort Cloud through millions of stellar encounters, through passing molecular clouds, through the solar system's repeated circuits around the galactic center. It is, in a meaningful sense, a survivor, a witness to deep time. When does that object stop being what it was and start being something else? If half the mass detaches as fragments, is the remaining nucleus still UN-271? If it becomes 10 large pieces, which one inherits the name? These aren't just semantic questions. They reflect deeper uncertainties about identity and continuity that astronomy rarely confronts. history offers partial parallels. Comet Shoemaker-Levy 9 fragmented into more than 20 pieces before impacting Jupiter. Each piece was tracked separately, given designations from A through W. But those fragments existed for only about 2 years between breakup and impact. UN 271's fragments, if they form, could persist for decades or longer. The Kreutz Sungrazer family consists of thousands of small comets, all believed to be fragments of a much larger parent body that broke apart centuries ago. They're observed as separate objects now. The parent is gone, known only through the orbital characteristics of its descendants. Is that UN 271's future? A family of smaller bodies replacing a giant? We tend to value preservation. Museums protect artifacts. Conservation efforts save endangered species. There's something viscerally upsetting about watching a unique object be destroyed, even when that destruction is natural, even when it yields scientific insight. The universe, however, values processes over objects. Stars explode, galaxies collide, planets migrate. Change is the constant. Preservation is the anomaly. UN 271 fragmenting wouldn't be a tragedy in cosmic terms. It would be an evolution, a phase transition from one state to another. The matter doesn't disappear. The information encoded in its composition remains accessible, potentially more accessible than before. But the object as a unified whole, that specific configuration of matter that has existed for billions of years, would end. There's another consideration that public discussion rarely addresses. Spectacular comet events attract public attention and funding. A boring perihelion passage where nothing interesting happens doesn't make headlines. Fragmentation, even if scientifically valuable, might not produce the visual spectacle that captures imagination. No dramatic tale, no bright coma, just a slow dispersal of material too faint for casual observers to see. Scientific value and public perception don't always align. What matters to researchers, compositional gradients, and isotopic fractionation, means little to general audiences. What captures attention, bright tales, and naked eye visibility, might be scientifically less interesting than subtle spectroscopic signatures from exposed interior material. The framing matters. UN 271 isn't just a visitor passing through. It's a system input, a massive injection of primitive material into the inner solar system that will interact with solar radiation, with the solar wind, with dust populations and plasma structures in ways we can observe and measure. Whether it arrives as one large nucleus or 100 smaller ones, those interactions provide data. The value is in the process, not the object. And here's the thing. UN 271 isn't the only thing rewriting assumptions this year. Across astronomy, across every wavelength and every scale, we're encountering phenomena that don't match our expectations. The models are failing, the predictions are off, and that pattern of surprises matters more than any individual anomaly. While everyone's been watching UN 271, something equally strange has been unfolding 65 light-years away. In late 2025, observations from the James Webb Space Telescope revealed unexpected molecular ratios in the atmosphere of an exoplanet designated WASP-121b. This is a hot Jupiter, a gas giant orbiting extremely close to its star, the kind of planet we've studied extensively because they're easy to detect and characterize. Their atmospheres are hot, extended, and transit in front of their stars regularly, which makes spectroscopy straightforward. Models predicted WASP-121b's atmosphere should be dominated by water vapor with trace amounts of carbon monoxide and methane in specific ratios determined by temperature and pressure equilibrium chemistry. The models have worked beautifully for similar planets. The chemistry is well understood. There shouldn't have been surprises. But JWST's infrared spectrograph found methane abundances 4 times higher than predicted, and carbon dioxide abundances significantly lower. The ratio is wrong, not slightly off. not within error bars. Fundamentally, inexplicably wrong. The first assumption was instrumental error. JWST is new. Calibration issues could produce spurious results, but repeated observations confirmed it. Multiple analysis teams working independently reached the same conclusions. The molecular ratios don't match equilibrium chemistry predictions. Something is breaking the models. Several explanations have been proposed. Maybe atmospheric circulation is more vigorous than modeled, quenching chemical reactions before they reach equilibrium. Maybe there are temperature inversions creating vertical stratification that models didn't account for. Maybe the planet's atmosphere contains clouds or hazes that are sequestering carbon dioxide through processes we don't understand. All plausible. All requiring revisions to models that worked fine for similar planets. The pattern is familiar. An anomaly appears at the extremes of observation. The initial reaction is to question the data, then to question the interpretation. Finally, reluctantly, to question the models themselves. WASP 121b matters because it's not unique. As JWST characterizes more exoplanet atmospheres with unprecedented precision, more discrepancies are emerging. Planets slightly too hot for their predicted compositions. Atmospheric escape rates that don't match ionization models. Chemical signatures that shouldn't exist at observed temperatures. None of these are crises. None invalidate decades of planetary science. But they're corrections, refinements, indications that our models, however sophisticated, are still approximations of reality. And approximations fail at the boundaries, at the extremes, at the edges of parameter space where we haven't had good data before. This connects to UN 271 in a way that might not be immediately obvious. Both cases involve large systems behaving differently than scaled-up versions of smaller systems. WASP 121b isn't just a bigger version of smaller hot Jupiters. UN 271 isn't just a scaled-up version of 10-kilometer comets. Size changes things. Scale matters. Physics that's negligible in small systems becomes dominant in large ones. Atmospheric circulation on a Jupiter-sized planet creates weather patterns impossible on Earth. Internal stress in a 140-kilometer comet creates failure modes impossible in smaller nuclei. The equations are the same. The phenomena are different. This is what frontier science looks like. Not catastrophic failures of understanding, but persistent, nagging discrepancies that accumulate until they force paradigm shifts. Thomas Kuhn described it in The Structure of Scientific Revolutions. Normal science operates within paradigms, solving puzzles using accepted frameworks. Anomalies accumulate. Eventually, the paradigm can't accommodate them anymore, and revolution occurs. New frameworks emerge. We might be watching that process play out in real time across multiple fields. Exoplanet atmospheric chemistry, cometary physics, cosmological observations that constrain dark matter models, gravitational lensing that produces mass estimates inconsistent with luminosity-based predictions. None individually overthrows established physics. Together, they suggest our maps of reality need updating. Astronomers are trained to be skeptical, to demand reproducibility, to question surprising results. This is healthy. Science without skepticism becomes religion, but skepticism can become obstinacy. And there's a point where accumulated anomalies deserve to be taken seriously, not as errors, but as signals, as indications that nature is more complex, more surprising, more interesting than our current understanding allows. The thematic link here isn't about specific phenomena. It's about the relationship between models and reality. Models are tools, simplifications designed to make predictions about complex systems. They're useful precisely because they simplify, but they're limited for exactly the same reason. When reality exceeds the model's assumptions, when you probe regimes where simplifications break down, surprises emerge. UN-271 is a surprise. WASP 121b is a surprise. The surprises are information. They're telling us where our understanding needs refinement. And the fact that we're detecting these surprises at all, that we have instruments sensitive enough and data rich enough to spot discrepancies between prediction and observation, that's new. We are living in a recalibration era. The universe hasn't changed. Our ability to measure it has. And measurement reveals gaps in understanding that were always there, but invisible until now. This should be exciting, not threatening. Every gap is an opportunity. Every anomaly is a question waiting for an answer. But here's the uncomfortable truth. Humans didn't spot these patterns alone. We had help. And that help is about to reshape not just what we discover, but how discovery happens. UN-271 was discovered by a machine, not in the sense that a computer physically observed it. Humans built the telescope, humans defined the survey parameters, humans designed the cameras. But the actual detection, the identification of a moving point of light in archival data from the Dark Energy Survey that was done by software. Software scanning millions of images, tracking objects across frames, flagging candidates that met specific motion criteria. Pedro Bernardinelli and Gary Bernstein developed the algorithms and analyzed the results. They deserve credit for the discovery. But they were working with a dataset so large, containing so many objects, that human inspection of every candidate was impossible. The software did the initial filtering. Humans confirmed. This is how astronomical discovery works now, and it's only going to accelerate. Modern astronomical surveys generate data at rates that exceed human processing capacity by orders of magnitude. The Large Synoptic Survey Telescope, now operational as the Vera Rubin Observatory, images the entire visible sky every few nights. Each image contains billions of pixels. Each night generates terabytes of data. Over its planned 10-year survey, it will detect billions of objects and trillions of separate observations. No human can look at that data directly. You need algorithms to process it, to identify transients, to track moving objects, to flag anomalies. And increasingly, those algorithms use machine learning, neural networks trained on patterns in existing data to recognize similar patterns in new data. This creates a fundamental shift in how discovery happens. Astronomy is no longer limited by how carefully a human can examine photographic plates, or how thoroughly a researcher can analyze spectroscopic data. It's limited by the quality of algorithms and the computational resources available to run them. Objects that would have remained hidden in data for decades, objects like UN-271 that move slowly and appear faint against the background stars, become detectable the moment software capable of recognizing their signatures comes online. The implications extend far beyond simple detection efficiency. Scale defeats intuition in ways that matter profoundly. Machine learning algorithms can identify correlations humans would never notice, patterns buried in noise that no amount of careful human inspection would reveal. They can spot subtle periodicities in time series data spanning years. They can classify objects based on multi-dimensional parameter spaces that human visualization simply cannot represent. We see in 3 dimensions, maybe 4 if we're clever about it. Algorithms work comfortably in hundreds. This isn't replacement. It's augmentation. Scientists still design the observations, formulate the hypotheses, interpret the results within theoretical frameworks. But the initial pattern recognition, the brutal computational labor of sorting signal from noise, the identification of candidates worth human attention, that's increasingly automated, and it needs to be. The alternative is drowning in unexamined data, while interesting phenomena scroll past unnoticed. Here's where it gets philosophically interesting. Machine learning models can, in principle, predict comet behavior. You train a neural network on observed comet-like curves, gas production rates, fragmentation events from the historical record. The network learns patterns, subtle correlations between observables and outcomes that might not be obvious, even to experienced researchers. Then you feed it new data from an approaching comet and ask for predictions about its evolution. Does this work? Sort of. Machine learning is excellent at interpolation, at predicting outcomes within the range of training data. It's terrible at extrapolation, at predicting behavior in regimes it hasn't encountered. UN-271 is pure extrapolation. No comet in the training set is this large. No observation in the historical record captures activity this far from the Sun during solar maximum. The parameter space is unexplored. The algorithm has no reference points. But that limitation is temporary and shrinking rapidly. As the datasets grow, as we observe more comets under more diverse conditions, as spacecraft visit more targets and ground-based surveys detect fainter objects, the models improve. Machine learning algorithms can already identify subtle precursors to fragmentation that humans might miss entirely. Slight changes in rotational period measured across months. Asymmetries in gas production that suggest structural weakness. Correlations between solar wind conditions and activity levels that wouldn't be apparent without processing thousands of data points simultaneously. The algorithms don't know why these patterns matter. They can't explain the physics. They just recognize that certain combinations of observables correlate with certain outcomes. It's pattern matching, not understanding. And there's something genuinely uncomfortable about that. Science is supposed to be about understanding, not just prediction. A neural network that correctly forecasts comet fragmentation 3 months in advance without explaining why isn't doing science in the traditional sense. It's doing something else, something powerful and useful, but philosophically unsettling. It's operating like an oracle, providing answers without justification, predictions without mechanism. And we're just at the beginning of this transition. More sophisticated algorithms are being developed that don't just recognize patterns, but attempt to generate hypotheses about underlying mechanisms. These systems analyze correlations, propose causal relationships, even suggest experiments or observations that would test their hypotheses. They're not sentient. They're not thinking in any meaningful sense. But they're performing cognitive tasks that used to require human insight, and they're doing it faster and often more thoroughly than humans can manage. The uncomfortable question that keeps surfacing in research discussions is this: how many UN-271s are already in the data, waiting to be found? How many anomalies? How many objects that don't fit standard categories? How many phenomena that challenge existing models are hiding in archival observations? Because no human has looked at that particular combination of data in that particular way. The answer is probably a lot. Potentially thousands of objects, events, correlations that would be scientifically significant. If noticed but remain invisible because the specific analysis required to detect them hasn't been performed. And as algorithms improve, as computational resources expand, as machine learning becomes more sophisticated in understanding what constitutes an interesting anomaly, those hidden objects will emerge from the archives. We'll discover things we didn't know we were looking for. We'll detect patterns we didn't know existed. We'll be confronted with phenomena that demand explanation. This fundamentally reframes what discovery means in modern astronomy. It's no longer just about building bigger telescopes or more sensitive instruments, though those remain important. It's about developing better algorithms, smarter software, more sophisticated analysis pipelines that can extract meaning from datasets too large for human comprehension. The bottleneck is shifting from data collection to data interpretation. We're drowning in information while thirsting for understanding. Some people find this transition threatening, even depressing. There's a romantic notion of the lone astronomer making discoveries through careful observation and brilliant insight. The individual genius connecting dots no one else saw. That model still exists in some corners of the field, particularly in theoretical work, but it's increasingly rare in observational astronomy. Modern astronomy is collaborative, computational, and heavily dependent on automation. But romanticizing the past misses the extraordinary opportunity in the present. UN 271 was discovered because software could search data humans couldn't process manually, not in a lifetime, not in a century. WASP-1 21B's atmospheric anomalies were detected because JWST's instruments, coupled with sophisticated analysis pipelines, could measure molecular abundances with precision that would have seemed like science fiction a decade ago. Progress comes from better tools, not nostalgia for simpler times when everything moved slower and we knew less. The fear that accompanies this transition, the worry that machines will replace human scientists entirely, fundamentally misunderstands the relationship between humans and algorithms. AI extends capability. It doesn't replace judgment. The algorithm can flag UN 271 as a candidate object worth examining. It cannot decide whether early activity indicates imminent catastrophic fragmentation or merely enhanced surface outgassing from localized vents. It cannot weigh competing hypotheses about solar-wind coupling mechanisms. It cannot write papers that interpret observations in the context of broader scientific questions about solar system formation and evolution. Humans and algorithms are good at fundamentally different things. Algorithms excel at pattern recognition in high-dimensional spaces, at processing vast datasets without fatigue or boredom, at maintaining perfect attention across millions of repetitive tasks. Humans excel at contextual reasoning, at creative hypothesis generation, at recognizing when basic assumptions need revision, at asking questions that haven't been asked before. The synergy between these complementary capabilities matters far more than either component alone. And here's the real insight that gets lost in debates about AI replacing scientists. UN 271 isn't a threat to Earth. It's not going to impact anything. It's not even going to become spectacularly visible to casual observers. What it represents is a diagnostic tool, a natural experiment in physics at scales and conditions we can't replicate in laboratories or simulate with complete confidence. The fact that we detected it early, that we're monitoring its evolution in real time, that we have the instruments and algorithms to extract meaningful data from its behavior, that's the genuine achievement worth celebrating. The solar system didn't change. Our ability to notice did. We've built observatories that can detect objects billions of kilometers away, moving at fractions of a degree per night against the stellar background. We've developed software that can search millions of images for patterns invisible to human perception. We've launched telescopes that can characterize exoplanet atmospheres 65 light-years distant with enough precision to detect molecular species in parts per million. We've created instruments that measure solar wind conditions with temporal resolution of seconds and spatial resolution of thousands of kilometers. And all of that infrastructure, all that technological capability built over decades, reveals a universe more dynamic, more complex, more surprising than we imagined even recently. UN 271 waking up early is just one example. A large example, certainly. A convenient example because it's happening now and we can watch its evolution unfold. But it's representative of something much larger than a single comet's unexpected behavior. We thought we understood comets reasonably well. We thought we understood atmospheric chemistry on hot Jupiters. We thought our models were adequate for the phenomena they were designed to explain. The universe is patiently demonstrating, through accumulated anomalies and persistent surprises, that adequacy isn't the same as completeness, that models are tools, not truth, that every answer we find generates 3 new questions we didn't know to ask. UN 271 will continue its slow approach toward perihelion over the next 5 years. It may fragment progressively into a distributed debris field. It may remain coherent against all expectations. The solar wind will continue to buffet it, to sculpt it, to interact with it in ways we're still learning to measure and interpret properly. And we'll watch, with instruments both human-designed and algorithm-enhanced, as this ancient remnant from the solar system's formation completes an orbital arc that began before human civilization existed, before our species evolved, before Earth had continents in their current configuration. The real story here isn't about danger or threat. It's about discovery, about what we learn when our tools finally become sophisticated enough to measure things we previously had to ignore or speculate about what happens when the universe reveals complexity we weren't specifically looking for, but stumble across anyway. About that crucial moment when unknown transitions from threatening to fascinating. When the correct response to, "we don't understand this yet," becomes excitement and curiosity rather than fear and denial. Because out there, beyond Saturn, in the cold and the perpetual darkness, something 140 kilometers across is either coming apart or staying together, or doing something we haven't imagined yet. And we get to watch, we get to measure, we get to learn. The comet doesn't know we're observing it with increasingly sophisticated instruments. It doesn't care about our models, or our predictions, or our interpretations of its behavior. It just exists, responding to forces, following physics, being itself in the universe the way all matter exists. Indifferent to observation, inevitable in its evolution, real in ways our models only approximate. And somewhere in the data streaming back from our instruments, in the patterns recognized by algorithms we created, in the spectra analyzed by researchers across continents and time zones, in the slow accumulation of measurements and observations and calculations, understanding grows. Not complete understanding, not final understanding, just better understanding than we had before, deeper models, more accurate predictions, fewer surprises eventually as our knowledge catches up to reality. That's what science offers. Not certainty, not comfort, not predictions that always come true or models that never fail. Just the systematic reduction of ignorance through careful observation and honest acknowledgement when reality exceeds expectation. Just the gradual construction of better maps of a territory that doesn't care whether we understand it or not. UN 271 is teaching us that our expectations about comet behavior need updating. The solar system is teaching us that scale matters profoundly, and size changes everything, and physics at the extremes contains surprises we didn't anticipate. The universe is teaching us, again, the same lesson it's been teaching for as long as humans have looked upward and wondered. We don't know everything. We never will. The universe is too large, too complex, too strange for complete understanding. But we can keep learning. We can keep measuring. We can keep building better instruments and smarter algorithms and more complete models. We can keep asking questions, even when, especially when, the answers challenge what we thought we knew. And out there, in the darkness beyond the planets, something ancient continues its journey inward. Waking early. Responding to forces we're still learning to map properly. Offering, through its mere existence and its unexpected evolution, a window into processes that shaped the solar system billions of years ago and continue shaping it now, whether we watch or not. The solar system didn't change. Our ability to notice did, and that changes everything.